Hello and welcome to the IOER-Forum. My name is Henrik Herold. I'm a senior researcher here at the IOER Research Group, Spatial Information and Modeling. I will be hosting today's forum entitled Towards a Science of Cities. For this, indeed ambitious topic, we have invited a distinguished expert, Dr. Marc Barthélémy. Bonjour et bienvenue sur notre forum.
Merci. Bonjour.
We are very pleased that you have followed our invitation. Thank you very much, and we appreciate even more since I know that is a holiday today in France. So thanks again.
No problem.
Okay, then. Now it's my great pleasure to announce and introduce Marc Barthélémy, our today's speaker. For those who don't know him yet, he is a physicist. He graduated in theoretical physics from the Université de Paris, which is, I think, now Sorbonne. After research stays in the US, he is now the research director of the EU leading Institute of Theoretical Physics in Saclay, which is near or close to Paris and Versailles. And besides this position, he is also affiliated to the Center of Social Analysis and Mathematics camps at the School of Advanced Studies in Social Sciences, the well-known EHESS. His research revolves around applications of statistical physics to complex systems, complex networks, epidemiology, spatial networks, and many more things. Marc has authored and co-authored more than 200 papers in high-ranked journals and also published several books on spatial networks and the science of cities. And so it's a perfect fit for today's topic. And now we are looking very much forward to the physicist view on the structure and evolution of urban systems that we also study. Yeah, Marc, the online stage is yours.
Thank you very much. Thank you for the invitation and this kind of introduction. Let me share the screen. Hopefully this is still working. Can you see it? Everything's all right?
Perfect.
Okay, thank you very much. So yes, thank you for this invitation. So I understood that the audience is relatively broad. So I prepared a speech which is mainly not a general speech, but not too technical. But of course, I'm happy to discuss more technical points afterwards. So I will try not to be too long. So I apologize in advance if some slides are far too simple for some people in the audience. So let me, I guess you are very familiar with all the slides. The first slides that you all see in all talks is that indeed most of the population is living in cities. This actually is nice because the data, I'm not sure how it was collected. It's the historical database. So this is the urbanization rate, and you can really see the sharp increase during the Industrial Revolution. And projections now are above 70% of the world population in cities. So indeed, it's an important topic and always more important, actually. And as you know, very likely, is that, of course, this phenomenon of cities happen all the time, I mean, for thousands of years and everywhere. And this large concentration of individual, actually the sum of all the area of all cities is approximately 3%, a few percent of the emerged land. So it's really a huge concentration of individual, allows for specialization, for exchange of good knowledge, etc. So it's naturally a source of wealth, of many innovations. So even if it's super concentrated, it's most of it's 80% of the world GDP. The patents, the innovation happen mostly in the city, etc. it's also a source of many problems. And we all experience congestion hours and traffic jam, which go together with gas emission, CO2 emission also. Cities represent approximately 70% of the world CO2 emission. And this figure didn't change for the 10 last years. And so the question is, of course, can we understand all this? Are these structures sustainable? How can we mitigate all these problems? And one way to do that is, of course, to understand the system quantitatively with models, and to understand in some sense the physics of the cities, meaning what are the main mechanisms? Can we really have some kind of intuitive understanding of what is going on? And with models, can we even get a figure? So that's really the main question. One of the problems is that the city is actually a very complex object, in the sense that it's made of many different constituents, individuals, organizations, companies, etc., that interact over many different time and spatial scales. And the result of that is that the outcome, the collective properties of a city are not obvious to predict. And this is typical from a complex system. You know the basic constituent, the microscopic element, if you prefer, but the collective behavior is not always easy to understand. So we see some spatial organization, segregation, for example, of course, congestion, some mobility pattern, etc. And these are really phenomena that appears at a large scale and result from all these microscopic interaction. So modeling cities is not an easy problem. And actually we can later discuss that. And I think this is the fundamental reason why it's not enough to construct a large agent-based simulation, some digital twin, for example, and to hope that, that the outcome of this numerical simulation will correspond to the reality. I think it's much more than just a collection of individuals. All the interactions are critical here. So the idea would be to use modeling for some aspect, at least, and to identify the important mechanism and the critical parameters. So on what parameters can we play to modify this and that. And so far, if I want to make a quick state-of-the-art slide, it would be this one. We can talk about urbanism, of course, and most of the, let's say, urbanism studies are really at the qualitative level and not very quantitative and not model-based. Urban economics is maybe one of the oldest scientific approach with regional science and geographer on cities. And usually the models are very simplified, which I like, which is nice. But one of the problems with economics in general and urban economics, that's very true, is that there's a very weak connection to reality. Is that you can, for example, the book by Krugman, Venables, and Fujita is 400 pages of calculations, but there's one single page about data. So this relation validating a model, the simplified model against data, that's unfortunately not super common in urban economics. So then, of course, many papers and a lot of work has been done on simulation. How can we simulate a city with typically agent-based models and the famous Luti models, and more recently digital twins trying to replicate a city numerically. And of course, there are many problems. I was talking about this complex system problem, the emergence of global behavior. That's difficult to capture. But in general, there are far too many parameters, and it's very difficult to understand the stability, the impact of perturbation, etc. And in fact, if I can give a very quick example, when the mayor of the city of Paris decided to close a segment of an urban freeway, Voie-sur-Berge in Paris, actually we had all types of simulation predicting one thing and the opposite. So even on a simplified problem, a world-posed problem. I'm closing a segment of an urban freeway in a big city. What will happen in terms of the traffic? We were not able to actually to predict what would happen. And maybe even worse is that a few years after, we still don't know if it was a positive or not a thing or not. So you see, this is why actually I'm a bit pessimistic about, you know, the possibility of making a large-scale simulation. But of course, we can discuss that later. Of course, machine learning is coming with all the problems inherent to machine learning, possible bias in the data, and also, of course, the black box effect, meaning that even if you have a result, you are not very sure why it is so and how it can improve your understanding. But that might change, of course, in the future. So today, I just would like to talk about another approach, which is, we can say, inspired from physics, which is trying to find the simplest model on a particular aspect. So we are not talking about simulating the city as a whole, just focusing on a very specific aspect and trying to put the smallest number of parameters and realistic mechanism. Because this could be one pitfall is that trying to propose a model in order to fit to the data, but that doesn't mean that the model is good. It's just that it's a model which is able to replicate your data. So I think it's an important constraint is that your mechanism in the model must be realistic and should correspond to some reality. And then the very important thing is that the prediction of the model should be verified empirically. This is what the urban economists didn't do. I mean, they didn't have enough data at the time. Now, I think that a big game changer is that we have a lot of data. And to me, one of the revolution is really mobile phone data and GPS. I mean, now we have mobile phone traces, which allow to, at an unprecedented scale, to observe how people are moving in a city. So I think this is really a revolution. We also can cross different files coming from the administration to have some specialized data. That's really great. And we can even now, with the digitalization of historical documents, we can even have a view over many centuries of how a city evolved. So that's really great. We have a lot of data at different scale for different processes. And so now when you have a theory, clearly you can, in most cases, check its validity. So this is why, I mean, we can hope to have some kind of physical model, let's say, or simplified model, and to test it against validity. And it's true that I'm originally a physicist, but in fact, there is a long history of physics and cities. And actually, some spin-like models were introduced by Schelling in 1971 to understand segregation. I will say a few words in a minute about that. But then in the 1980s, it was the big time of DLA and fractals. So at that time, some physicists like Jean Stanley and some geographer like Denis Plumin measured the fractal dimension of the city, proposed some models, DLA-like models for the growth of cities, etc. And percolation as a tool also is actually a very interesting. It's coming from physics and invaded the definition of a city was proposed as a percolating cluster by Max and Rosenfeld et al., etc. And even these last 10 years, we had some model directly inspired from physics, like the radiation model, to explain mobility between counties or a different scale. And before that, in fact, the gravity model is directly coming from the gravity formula from Newton. So there's really a long tradition, let's say, of exchanges between physics, geography, and let's say regional science. And stochastic models is even, I think, more important and was really at the crux of understanding cities and the growth of population. And today, I will try to talk about a few of these examples to illustrate this type of approach. And again, not at a very technical level. So, and let me start with the historical model, because I think this is really typical of what a physicist could do, although Schelling wasn't a physicist at all. But this is really, in the 70s, although it was the great era of statistical physics, but apparently at this time, the people like Schelling didn't speak really to physicists, and conversely, I mean, in the 10 references giving, there's none of of physicists. So I think the interdisciplinary barrier, were very strong at that time, and his goal at that time was really to understand why there is segregation in cities. And for the US, and Schelling was in Harvard, it was basically the black and white segregation in large cities, the problem. And you can model this by 3 states, +1, -1, and vacant. And the model is extremely simple. It's really in the spirit that of things that we want to do, is that you look the fraction of different neighbors. So here on this guy I is surrounded by 4 guys of the same type and 3 type different. So the fraction of different neighbor is actually 3/8. And you look this fraction and compare it to your tolerance. So if your tolerance, so if this fraction is less than your tolerance, you are happy and you stay. If it's larger, you are not happy with your neighborhood and you move to another place. So this is really a very simple model. And here I give some more recent simulation. And what's happened is that when the tolerance is very small, you are in a kind of mixed state. And but when you increase the tolerance at a certain point, what happens is what we see here is there is some segregation. Is that people are not satisfied with their neighborhood and they move, and collectively what happens, even, and that was the point of Schelling, even if your tolerance is relatively large, in the Schelling model it was 1/3. What happens is that still you see segregation. So even if all guys individually are relatively tolerant, what happens is that at a larger scale, if you wait long enough, you will see some segregation. And that's really, I think, that really highlights this link. So for Schelling, it was micro motif and macro behavior. So in statistical physics, it's really the passage from, let's say, from microscopic constituent to macroscopic and global behavior. It's not a trivial thing. Even if you have some relatively simple microscopic behavior, it's not always clear what it will give at a large scale. And so I think this is why we should be very careful with modeling cities. It's not just a collection again of constituent and some behavior. Things can be much more difficult. And in physics, we have for example, if you know everything about the H2O molecule, the water molecule, it's not easy to make a simulation that will predict that it will form a nice crystal at 0 degrees Celsius. So this collective behavior, again, is not a trivial thing. So this was some kind of historical example of this type of approach. And of course, I have to speak about, of course, the spectacular example, which is the zip flow. And actually, the origin of this zip flow was a German physicist, Felix Auerbach, and he was really a precursor of interdisciplinary work. He worked with Helmholtz and other Kirchhoff, if I remember well, and worked on vocal sounds, and also got some interest with on cities. And he was, a friend with famous artists such as Munch. So there is actually a nice painting of him by Munch. And Auerbach had some idea, sorted the population of the cities, of German cities at that time. So at that time, the largest one was Berlin. So the first column, this is in 1,000. So Berlin at the time, 3.5 million approximately, then Hamburg, Leipzig, etc. And he had the idea to sort these cities and then to multiply the rank by the population. And this is what S times the rank R. So the first city has the rank 1, etc. And he found this is the original drawing. So, so if you speak German, you don't need the translation in blue. And what you see is that versus the rank, what he called at that time the absolute concentration is relatively constant around 50. So he noticed really this rule that population times its rank is approximately constant. And this was redone 20 years, more than 20 years after by Zipf, an American. And here I show you the plot for metropolitan for MSA, I think in the US. And he found more or less the same thing, is that the population is sometimes not exactly 1 over the rank, but close. And this is, of course, super important, because if you know the largest city and the rank of other cities, you can predict their population. It also tells you, for example, that the size of the largest city in a country is more or less twice as large as the second largest city. And the thing is that Zipf did this on many things. I don't have the time, but he did this for the occurrence of words in books, etc. And this is for the James Joyce Ulysses. And he found the same law. And this is why it's called Zipf law in general. The fact that the quantity is going like 1 over the rank, more or less. But for cities, it's really Auerbach who did this the first time. And of course, you shouldn't be confused by the fact that Zipf law is relatively stable. It's a statistical law, and you can observe it on different epochs and different countries. But still, the dynamics of cities disappear, and some happens rise and become super important. Here, this is the rank clock proposed by Batty some years ago, and typically so it's clockwise. The time is going from minus 400 BC to 1950 approximately. So you have to turn clockwise, and the radius is actually depends on the rank. So the closer it is to the external boundary, the more important it is. And so you see that you have huge fluctuations in the rank. So some cities that were super important 100 years ago are not existing anymore. So you really, this is the dual problem in some way, is that you have a relatively constance of a result, which is the Zipf law, statistical regularity, which is more or less correct. And in the same time, you have a turbulent dynamics. And so you really need to reconciliate how can we understand the Zipf law and this turbulent dynamics. And so what are the main mechanisms that could explain that? And I have to add at this point, but we can discuss this later, is that Zipf law was, with the availability of new data, people started to criticize the Zipf law, that it's not really working for some countries, that it's not always a power law, that the exponent is unclear, there's some curvature. So the Zipf law, in fact, is not working that well. And there was a nice meta-analysis of Zipf law done by Clémentine Cotineau, and she clearly showed that indeed Zipf law is not the universal result that we would like to have. But still there's some relatively statistical regularity, and it all points to the problem, which is what's the equation describing the evolution of urban population? This is very general, but what is it? And this is clearly, it took us more than 100 years to discuss that. And one of the important names, of course, is Gibrat with the growth of firm. And then the model was adapted by an economist called Gabet. And so there's a very, very long story. But just to give you a hint of what we did more recently, is that we just looked at the sources of growth of a city. And so if you take a system, which is a country, typically, could be something else, could be Europe or some, let's consider the country. a city actually is growing from 3 sources. The first source is the natural growth, which is typically the difference of birth minus death. That's the first term. Then you have some international flow, people coming from abroad, from another country, going directly to the city. And then there is another term, which is typically the interurban flow, people moving from one city to the other one. And so what you could write is that the variation, the time variation of the population of city I, let's say, is the sum of these 3 terms: natural growth, international flow, and interurban. And the good thing, and really here we don't speak about the zip flow or whatever. We just would like to understand why, how is the variation of the city urban population. And the nice thing is that we can study these different terms empirically. We have the data now. So maybe 20 years ago, it was probably extremely difficult, but now we can do it. And basically, the result is that we could actually write the equation, simplify these different terms, and write the equation, evolution equation for the urban population. And the main result, and so I can just discuss later this equation, but the main result is that we have basically 2 main terms in the growth of cities. First, the demographic growth, again, which is the birth minus death budget, typically balance. And so this is typically random with small fluctuation. And for experts, this corresponds to typically the Gibra term with a multiplicative noise term. And this is typically the first term of the equation. And if we add this, all cities would grow with small randomness, actually, and the rank would never change. We could observe something close to the zip flow, but this is absolutely unable to explain the large fluctuation. And in fact, and that was the surprise, is that the most important, in fact, term here are interurban migration. This is typically a random term, people moving from a city to another one, but sometimes with huge values compared to the size of the city. And this is really what explains the turbulent dynamics of cities, is that for some reason people arrive all of a sudden, for example, in San Francisco, because there is a gold rush in 1850 or so, or people just go away because some mining industry closed, etc. And these random events, which are really huge, so we can call them shocks, in fact, are described in this second term of the equation, and actually are able to explain the turbulent dynamics. And so I think that, maybe 100 years after, we understand why zip flow is not always valid. And it's, in fact, in the best case, it's an approximation. And second, that what is the, let's say, and that the most important term are actually interurban migration, which also is a positive message, because it means that the fate of a city is not written in stone. If we had only the small fluctuation, cities would grow, business as usual. But here, these shocks really shows that, innovation, opportunities, and things like that are really important. And planning and governance have really a major effect on the fate of a city. So I think that's really the important message. So you see here that it's a rather theoretical and general question, but we are still, ending up with some more concrete conclusion. So I wanted to speak. Do I still have 5 minutes or something like that, or let me know?
Yes, that's fine. Even more.
Okay. So I wanted to give you, so I go quickly. So this was the one important example, but we can have a more practical example. So for example, some very specific questions, such as how many car users are in your city? And for this, so I show you this model because the conclusion is actually kind of simple and surprising. So for example, imagine the question, so shall I take the car or the subway to go to the office? That's a very simple question. And we assume that there is a probability P to have access to a subway station. To have access means that you are not too far. And typically, it could be half a kilometer or kilometer. That's not super important, but you should be able to walk to the subway station. And so then the super simple, simplistic model would be this one, is that with some probability 1 minus p, you don't have a subway station in your immediate neighborhood. So then you would take the car to go from your position X here to the office. That's very simple. In case there is, with probability p, a subway station, then you can either take the metro or go directly to the office by car. And in this case, you have to compute the cost, in some sense, of these two different mode choice. And the cost is some combination of the financial cost, of course, but also the time it will take to go there. So, of course, this will depend if you go in the details. This could depend on the income. Of course, some people prefer to spend more money, but to go fast. As some people have less revenues, smaller income, and they will spend a longer time to go to the office. So anyway, you have these two cases, and then you can try to compute in the framework of this simple model, the traffic, which is the number of people taking their car, versus the population, total population of the city. And this model gives you an equation, so I didn't give it here. And in fact, in large cities, it even simplifies to the super simple equation that I wrote here, meaning that basically the people in large cities where there's a lot of congestion, the ones who are taking their car are basically the ones that are not close to a subway station. I know this is super simple, but it gives you this very simple, the number of car users is basically the probability not to have the fraction of people not being close to a subway station times the population. So, of course, in front of such a simple result and simple model, you have to check versus the data. And I think the surprise is the next year. So we found the data for almost 30 cities. And I would like to insist on the fact that this is not a fit. So the prediction of the number of car users of the population, so the share of people taking the car, is given by 1 minus p, where p is the probability to be close to so you can compute this quantity or get some data for it. And so this is the red plot, and here the red line, and here are the dots for the symbols for all the cities. And you see that it's not bad. Actually, that's the really surprising thing, is that now we have a relatively realistic mechanism, a minimal number of data. Actually, we are not tuning any number here, and we get a relatively good prediction, in fact, of the percentage of people taking the car. So I don't say that's the ideal model, etc. I just wanted to show you this because it gives you a flavor of the kind of model I actually like, and I think that are useful because they allow to extract the critical parameters. So that's a very simple example. And you can go a little bit further, and even with this model, you can compute the quantity of CO2 emitted per capita. And you see this model tells you that it's a product of three terms. It's also, you can see it as the consumption of gas, also the gasoline consumption. And in fact, these three terms are basically the size of the city, the probability, the density. The first term is 1 minus p. It's the density of public transport, typically, and then there's some congestion effect. So it also means that there are different conclusions for those who know the Newman-Kenworthy curve, where the energy, the gas consumption per capita versus the density. So there's this nice plot by Newman-Kenworthy. It's actually totally wrong and cannot be justified by the theory. Here it's more complex, and the public transport density is the most important. And in fact, if you want to decrease emission, this equation tells you that you don't have to increase density randomly, but you have to increase the density around access point of the rapid transit. And this is actually known, it's the transit-oriented development, but increasing blindly the density in a city is not working. You really need to increase the access to public transport. So again, from such a simple model, but which we can validate actually against data, we can get some conclusion which are maybe not all new, but at least that are robust and validated by data. And so let me finish with a small example. It's about subway. It's because I like this system very much, and so this is already all the plot where we see the proportion of cities with a subway system as a function of the population. And basically, this is already dating this older picture, but above a few million, the majority of cities have a subway system. So it's really something that appears quite automatically above a certain population. Here's an example, Paris, of course, and on the right here, you have the physical network, and on the left, the designed network, which is, of course, is not the same. So you shouldn't use this design map actually to move around in a city. It could be very misleading. And the thing is that it has been observed for all these subways that the shape is actually varying with the total length. So one important indicator is the total length, which is a good proxy for the cost of this system. Because we are talking usually about millions euros per kilometer. So it's really the total length is really a good indicator of the cost. And typically, this is what we observe. For small network, you have basically a line. If you increase the length, you see some ring structure appearing, some loop. And for larger network, you see more complex things such as a ring and radial lines, this sort of thing. And actually, we focused on the largest subway network in the world. And we realized, it's not always easy to see, but that they have, in fact, the same structure. And so you can test that. But basically, the structure is kind of a spider with some core and some branches. And in fact, if you detect the terminal station, you can prune the network by removing this and stop at a certain point when the degree is larger than a certain value. So there is a non-ambiguous way with a computer to remove these legs and to get the core. And this is how we could show that the largest subway network in the world have this sort of structure. And it's not just the topology, but in fact, it's some sort of quantitative convergence in the sense that the numbers are more or less the same for all these large networks. So for example, the number of stations in the branches is of order of half of all the stations. The size of the branches over the size of the core here is typically of order 2, etc., etc. So there are different numbers. So it's actually here. This is a more empirical work, but we observe this striking fact that there seems to be a universal shape for the large networks. Of course, I probably get question on that, but this is not working where you have strong constraint. For example, for Chicago, there's the lake, and so it's pushed on the west side, etc. But for large network in general, we observe this, and in fact, we try to understand this. And I just would like to mention this, but we ask ourselves what would be the shape of an optimal subway. So if we could construct the subway from scratch, knowing the population density, what would be the optimal shape? And so you can solve this more or less easy. It's not that easy, but you can try to solve it numerically. But it's interesting to observe that it's mathematically, it's a completely open problem. It's really relatively unknown, and we looked at simplified and very specific case with David Aldous, an American mathematician, and we looked, for example, this sort of system with different branches and a ring, and we were increasing the size L, the total size of the system, and we observed something interesting, is that typically when you increase the size of the system, the best shape is usually some kind of star graph, radial branches going from a center. But at a certain point, when you continue to increase the total length, so the money available, it becomes actually better to construct a ring instead of making these branches longer. So there's really some sort of a transition at a point where where a ring appears. So it's interesting to observe that for this optimal structure, there is naturally a ring appearing, and this is what you observe in reality. So I don't say we have a model here and we understand everything, but it's this mathematical consideration shows us that the resource go preferentially first to radial branches and then to the ring. So I think that's an interesting point, but we still don't have a model for the growth of subways, actually. So let me, this is my last, I'm sorry, I was a bit late, my last slide. So I tried to convince you, if you are not convinced before, that cities are really complex systems and evolving in time. I think that's an important point, especially after having decades of economists working on the system in equilibrium. I think it's far from equilibrium, cities, actually, and they don't have an optimal shape. You have a whole hierarchy of cities, and you have some path dependency. So the shape of your city depends on its history and what was built before. So typically, these complex systems are very likely the most complex system that human built. And they combine so many difficulties that, we are, I think, far from a very good modeling of these systems. However, I'm still optimistic, and I think that the availability of data and some interdisciplinary approach, so I think some, joining with economists, geographer, mathematician, etc., we can solve some aspect. And here I try to advocate this approach of parsimonious models that allow us to understand something in the data and to, let's say, to highlight or to extract the critical parameters, and to actually, by testing the validity of our prediction, we can indeed test if our ideas about the important mechanism are correct or not. So if your model is not working, then you missed something important. And this is how physics did for centuries, actually. You're proposing a model, and if the predictions are good, you're happy. If the predictions are not good, you go back to your desk and try to think why it's not working. And I think we can make this loop between data and empirical measurement and theory. And of course, the crucial ingredient is the data availability. And unfortunately, it's still not easy to get. For example, mobile phone data is not super easy to get. Some institutions in some countries, and I can say that in France, for example, it's extremely difficult to get data, even by institutions. Try to get the data from the RATP in Paris or the French railway, the SNCF. And traffic data is the same. So some countries are definitely not playing the game and are not sharing the data. So data availability, I think, should be really discussed, and in my opinion, should be the first thing to put on the table before some big planning project. We had this Grand Métro, Grand Paris Express, this big project of a large subway around Paris. And it's surprising to see that data was not the first thing that people were discussing about. So, but I think that's a major problem. Of course, whatever modeling you want to do, and of course, then there's machine learning, digital twins. So there are some new candidates for understanding this complex system, and they might play an important role in the future. So I will end on this, and just signaling that I wrote a book about this ZIP problem and statistic of urban population with my former student Vincent Verbavats, and this should appear soon. So thank you very much for your attention, and sorry for being a bit long.